Hello everyone, today we are talking about generalization, one of the most complex concepts in machine learning. To me, I think generalization is the bridge between trained models and real-world solutions. If your model, if your AI product or AI agent is not able to generalize to unseen datasets, it is not useful in a real-world situation. It needs to be tuned to make sure that it's able to behave as expected or accurately using unseen datasets. The reason why generalization is one of the most complex concepts in machine learning is because we only train our model on a small subset of the actual data. Now, the actual data, the real world data, in most cases, is unmeasurable. It's terabytes of data. You cannot really measure the data. So now your model, even though trained on a small data set, it should be able to perform as expected on a larger real world data set. This is where deep learning shines. Most of the deep learning models, they go beyond statistical performance. They go and find the underlying behavioral patterns in the data, then they are able to predict. For example, let's say your model is trained on USA roads in the United States of America. If you take that car and drop it in a different situation, let's say somewhere in India, and it's now driving in the Indian environment, will that car be able to operate as expected in the US as also the same as expected in the Indian roads? That's generalization. Is it able to take what it learned and apply in different situations? All right, so we're going to discuss why it matters, why it's hard, and how a machine learning developer can master it. Now, formal definition of generalization is a model's ability to perform well on unseen data, not just the examples it was trained on. It's the difference between memorization and truly learning the patterns. We want our model not to overfit or underfit. We want a perfect fit of the model on the real data. All right, so generalization is complex because there's issues to do with the bias, variance trade-offs, distribution shifts, model capacity, and data size. As I said, you cannot really predict or measure the actual data in the world out there. Real world uncertainty in the real world is different from the lab where you train your model on. The real world, there are many variables that affect the data, the noise that comes into the data. There's a lot of probably now values that comes with the data, and your model should be able to perform way better when in the real world. All right. Now, the whole concept of generalization lies on the mean squared error. A small error indicates a robust model that has learned generalizable patterns, while a large error signifies overlifting. The model memorizes training data instead of learning the underlying structure. We want our model to learn the underlying structure. All right, I'm trying to move a little bit faster to get to the PowerPoint, to the Python code that I am using. All right. Techniques to improve generalization, of course, regularization, data augmentation, using different models or assemble models, cross-validation, early stopping. Now, early stopping is just basically stopping the training before overlifting begins. Then transfer learning, leveraging pre-trained models brings generalized knowledge from large-scale datasets to your specific task. All right. Now, I talked about self-driving cars, recommendation systems. Let's talk quickly on recommendation systems. Now, user preference evolve constantly. We humans, we are not machines. My interest today during the Christmas period, I might be searching on how to decorate a Christmas tree. But in January, I might be searching or working on how to deal with snow. Then in the spring, I'll be talking something else. Will your model be able to adapt to shifting test trends and patterns that are emerging? All right. Theoretical foundations, most of you know PSC learning framework, the 3C dimensions, generalization bounds. All right, I want to quickly jump here to my PowerPoint, my Python query here, just a generalization example, and I would want you to check this diagram that I have. This is my X and Y. All right, so I have three models here. I've got the linear regression model, which is in this straight line. Then I have this orange one, which is kind of curving in nature. Then a polynomial degree 15, which is this green line. It's kind of wobbly. All right, so the green dots are my test data, and the red one, the green dot is the training data, and red is the test data, green and red. Okay, perfect. All right, so let's talk briefly on linear regression, this straight line that we see right here. All right, so you can see the training mean squared error is 39.94, the test mean squared error is 50.19. All right, let's Before I call and explain these numbers, let me just generalize on mean squared error. Mean squared error measures the average squared difference between predicted and the actual values. Most of you know the formula. Now, lower mean squared error, it basically means a better fit to the data. A higher mean squared error means overfitting. Right, perfect. So, linear regression training, which is the straight line that we see right here, from here. Mean squared error is 39.94. 39.4 to me, the model doesn't fit the training data very well. It's actually underlifting. Now, the test mean squared error is 50.9. Performance on unseen data is even worse. It's actually higher. We want the mean squared error to go a little bit lower. All right. So what we can say just by looking at the mean squared error is that our linear regression model, if with a high bias, low variance, or the model is basically too simple. All right, let's talk about the polynomial degree 4. Our trained mean squared error is 18.4. So this is the orange one. And test mean squared error is 21.32. All right. 18.92 fits the training data better than linear regression, so it fits better than this straight line that you see. Then the test mean squared error is 29.32. The test error, as you can see, is closer to the trained mean squared error, meaning it generalizes well. So I would say the orange line, from what we have seen so far, the linear and the polynomial degree 4, which is the orange line, the orange line is a balanced model. Bias and variance are both kind of moderate. All right, polynomial degree 15, we have our trained mean squared error of 11.96 and the test mean squared error of 39.88. Now, trained mean squared error of 11.96, it means a very low error on training data, which we have discussed. It almost perfectly fits the data. And the test mean squared error 38.88, the test error jumps significantly. If you can see, the green one is kind of tries to hit all the trained data sets. It's kind of overfitting, low bias but extremely high variance. It doesn't generalize very well when we expose this model to unseen data. So as a machine learning developer, this is what you'll be looking at. You would want your models, your trend, both your trend mean squared error and the test mean squared error to be lower. Basically, for linear regression models, I would say around the 20s. Then for ideal test, mean squared error, we still want it to be around 20 for linear regression. For polynomial degree, I would say between 18 and 20. Let it play around 18 and 20. Then the ideal test mean squared error for polynomial degree, I would want it to also rest between 18 and 22. Polynomial degree 15, I would want the ideal training mean squared error to be between 12 and 15. And then the ideal test mean squared error, I would want it to be between 18 and 22. I'll put these numbers on the screen so that you can have reference. Now, if it's between 18 and 22, it means training mean squared error is good. Test MS is too high. It reduces complexity and improves on generalization. I hope this video helps on how to interpret the results and your models. We want your models to be moderate. We want your models to be able to be